When people hear air defense, they usually imagine a missile launcher firing at an incoming target. But that's not how modern air defense actually works. An integrated air defense system isn't a single weapon, it's a network. Sensors, radars, command nodes, shooters, and decision makers all link together in real time, often across hundreds of miles. In this video, we're breaking down how integrated air defense systems actually work, why they're so difficult to defeat, and why controlling airspace today is less about individual missiles and more about coordination, data, and time. If you want clear, no-fluff military breakdowns like this, make sure to like the video, subscribe to the channel, and drop a comment below. Modern air defense is not built around a single interceptor or a single radar. It is built around integration. An integrated air defense system, usually called an IADS, is a layered network designed to detect, track, identify, prioritize, and engage aerial threats across an entire battle space. Its strength does not come from any one weapon, but from how sensors, command nodes, and shooters work together. If you want to understand why modern air defense is so hard to beat, you have to stop thinking about it like a missile launcher and start thinking about it like a living organism. It sees, it thinks, it decides, and it reacts, sometimes in seconds, sometimes across hundreds of miles. At its core, an integrated air defense system is a system of systems. Early warning radars search long distances for potential threats. Tracking radars refine that data into something accurate enough to fight with. Then command and control nodes fuse information from multiple sensors into one picture that decision makers can use. Engagement radars cue interceptors. Shooter units launch based on doctrine, rules of engagement, and the tactical situation. Every part feeds the others. That is the point. Integration lets defenders see farther and react faster. It also lets them conserve resources by engaging the right targets with the right weapons at the right time. And in modern air defense, wasting interceptors is not just inefficient, it is fatal. The cycle starts with detection. Detection is not the same thing as engagement, and most people mix those up. Early warning sensors exist to buy time. They are there to find something before it becomes an immediate crisis. These sensors can include large ground-based radar arrays, long-range surveillance radars, over-the-horizon systems, airborne early warning aircraft, and space-based sensors that detect launches or hot exhaust. They can also include passive detection systems that listen for emissions rather than blasting radar energy into the sky. The point is not to shoot first. The point is to know first. Early warning gives commanders options. It allows forces to disperse, aircraft to launch, missile batteries to reposition, and command nodes to shift their posture. It also allows leaders to decide whether what they are seeing is a real threat, an accident, or a deliberate probe. In air defense, time is the currency. Everything else is built on how much time the system can buy itself. Once something is detected, the next problem is tracking. Tracking is the difference between knowing something is out there and knowing where it is going. Tracking radars refine the picture by calculating speed, altitude, heading, and behavior. This is where a random contact becomes a target quality track. But tracking alone is not enough. You also need identification. Identification is where air defense becomes as much about politics as physics. Is this friendly? Is it neutral? Is it hostile? That sounds simple until you remember that many aircraft can look similar on radar. Cruise missiles can fly low and hide in clutter. Drones can be small enough to blend into the background. So identification relies on multiple methods. It can include IFF responses, flight plan correlation, emissions analysis, behavior patterns, and confirmation from other sensors. This step is critical because the cost of a wrong decision is enormous. Engage too early and you waste interceptors and reveal your position. Engage too late and the threat gets through. And if you hit the wrong aircraft, the consequences can be strategic. One mistake can destroy legitimacy, fracture alliances, or trigger escalation. This is why integrated systems matter. A single radar can lie to you. A single sensor can be jammed, spoofed, or simply mistaken. Integration lets multiple sensors look at the same contact from different angles. It allows data correlation, cross-checking, and confidence building. Instead of one radar telling the story, the network tells the story. That story then flows into command and control. This is the brain of the IADS. Command and control nodes take in sensor data from across the network and fuse it into a common operating picture. Operators can see tracks, predicted routes, altitude, speed, threat categories, and engagement zones. This is where prioritization happens. Because in a real fight, you will have more inbound threats than you have interceptors to waste. So the system has to decide what matters most. Is the threat headed toward a high-value site? Is it a decoy meant to pull interceptors away? Is it a weapon that must be killed immediately because it carries a strategic payload? This is also where doctrine shows up. Some IADs are built around centralized control, where higher headquarters approves or directs engagements. Other systems use decentralized authority, allowing local batteries to engage autonomously when time is short or communications are degraded. Centralized control is efficient. It prevents multiple batteries from engaging the same target unnecessarily. It helps allocate interceptors based on probability of kill and weapon availability. But it creates a vulnerability. If you can disrupt the brain, you can cripple the body. Decentralized control is resilient. If higher headquarters is jammed or destroyed, local units can still fight. But it can be inefficient, with multiple shooters chasing the same track or wasting interceptors on low-value targets. Most modern systems try to blend the two. They want centralized coordination when the network is healthy and decentralized autonomy when the network is stressed. That flexibility is what keeps the system alive under attack. Now we get to the part most people think is the whole story: engagement. Engagement is the action piece, but it is only one stage in a long chain. In a true integrated system, shooters do not hunt blindly. They are cued by sensors elsewhere in the network. That means a missile battery can stay quiet, hidden, and survivable until the system assigns it a target. This matters because emitting radar energy is like turning on a flashlight in a dark room. You can see, but you can also be seen. Modern air defense tries to minimize that exposure. Shooters often rely on remote cueing, brief emissions, and rapid displacement after firing. Engagement also depends on layering. Different threats require different weapons. Long-range systems exist to engage high-altitude aircraft, large ISR platforms, and in some cases, ballistic missiles. Medium-range systems target strike aircraft, standoff weapons, and cruise missiles depending on their flight profile. Short-range systems and point defenses protect specific assets against drones, loitering munitions, helicopters, and saturation attacks. This layering forces attackers to solve multiple problems at once. Even if they avoid long-range systems, they may still face medium and short-range systems as they get closer. Even if they get a few weapons through, point defense might still save the high-value site. That is the design. No single layer has to be perfect. The network just has to remain dangerous. After engagement comes assessment. And this is where a lot of people underestimate how hard the job is. It is not enough to fire and assume. The system has to verify. Was the target destroyed? Did it break apart? Did it maneuver and survive? Did debris create a secondary hazard? Assessment feeds back into the network immediately. If a kill is confirmed, interceptors can be conserved. If the target survives, the system must decide whether to re-engage and with what. That re-engagement decision is where integrated systems become especially difficult to overwhelm. They are not just shooting. They are adapting. Now here is the concept that explains why an IADS does not need to be perfect. Denial. An integrated air defense system is designed around one central principle: denial. It does not need to destroy every incoming aircraft or missile. It only needs to deny the attacker freedom of action long enough to change strategic outcomes. That denial can take multiple forms. It can force aircraft to fly lower, which reduces their sensors and increases vulnerability to shorter-range weapons. It can force strike packages to launch from farther away, reducing payload effectiveness and increasing the number of aircraft required. It can slow the tempo of operations, and slowing tempo can be decisive because modern air campaigns are about sustained pressure. If you disrupt that pressure, you change the war. Even partial denial can have strategic impact. If an attacker cannot guarantee safe access to airspace, they begin to ration sorties. They begin to avoid certain targets. They begin to accept slower timelines. And timelines matter because wars are political. Every extra day of risk and cost changes political will. This is why integrated air defense systems are built to survive, not just to kill. Survivability is the hidden advantage. Survivability comes from redundancy. Multiple sensors, overlapping coverage, backup command nodes, alternate communications paths. If one radar goes down, another may still provide queuing. Survivability also comes from mobility. Modern air defense units relocate. Radars can displace. Launchers can displace. Command nodes can displace. Mobility creates uncertainty. An attacker may detect a radar, plan a strike, and then find the radar has moved by the time weapons arrive. Now the attacker has wasted time, burned weapons, and gained nothing. That constant repositioning also forces the attacker to keep searching. And searching requires aircraft in the air, sensors exposed, and time spent. Time spent is cost. Survivability also comes from emission control. A disciplined IADS does not leave radars on all the time. It uses passive detection, remote queuing, and brief emissions to reduce exposure. This complicates anti-radiation weapons. If a radar only emits briefly, the attacker may not get enough time to lock and kill it reliably. And even if they do, there may be another radar or another sensor feeding the network. This is why suppression of enemy air defenses is not a one-and-done event. It is a campaign. Attackers have to do multiple things at once. They have to blind sensors through electronic attack and physical destruction. They have to disrupt command and control through jamming, cyber operations, or strikes on nodes. They have to saturate the system to force it to waste interceptors. They have to force radars to emit so they can be targeted. They have to hit mobile launchers that can relocate after firing. And all of that has to happen while the IADS is actively fighting back. Because unlike static targets, an IADS is reacting in real time. This is where the network aspect becomes the real battle. The fight is not just in the air, it is inside the kill chain. Attackers try to break links in the chain. If they can disrupt detection, defenders lose time. If they can disrupt tracking, defenders lose accuracy. If they can disrupt command and control, defenders lose coordination. If they can disrupt engagement, defenders lose lethality. If they can disrupt assessment, defenders may waste interceptors re-engaging targets that are already dead. Defenders, meanwhile, try to keep enough of the chain intact to remain credible. Because credibility is a weapon. If the IADS remains credible, the attacker cannot behave freely. They have to plan around it. They may choose different routes. They may choose higher altitude or lower altitude, each with trade-offs. They may choose standoff weapons that reduce risk but increase cost and limit payload. They may shift to drones and decoys to probe, which slows operational tempo. They may accept that some targets are not worth it. That is denial in action. The odds is shaping the attacker's behavior. This shaping effect is why integrated air defense is central to modern deterrence. It raises the price of intervention. A state with a credible IADS can make outside actors think twice. Not because it guarantees victory, but because it guarantees pain. It guarantees uncertainty. It guarantees higher losses, higher costs, and longer timelines. And that may be enough to prevent action in the first place. When conflict does occur, an IADS shifts from deterrence to denial. Its objective is to prevent air dominance. Air superiority enables speed and freedom of maneuver. It enables deep strikes, rapid movement, and precise targeting without constant fear. If an IADS keeps airspace contested, it forces caution. Caution slows everything down. Logistics convoys have to move differently. Ground forces have to disperse. Command posts have to hide. Aircraft have to fly different profiles. Even an advanced air force becomes less efficient when forced to operate under constant threat. This is why modern IADS investments are so strategic. They do not just protect the sky, they reshape the entire battlefield. Integrated air defense also rarely stands alone. It is often combined with fighters, airborne early warning, and even naval sensors. Fighter aircraft can extend detection and engagement farther from defended areas. They can intercept threats before they reach the missile belts. They can also act as sensors, feeding data back into the network. Naval radars can contribute long-range tracking and cueing, and especially in coastal environments. Ground forces can provide visual confirmation, local radar coverage, and protection of key nodes. This combined system is what makes modern air defense difficult to dismantle quickly. Even if one part is degraded, other parts can compensate. And compensation is the core theme here. Integrated systems survive by adjusting. That adjustment can be procedural, like changing engagement doctrine. It can be technical, like shifting frequencies or using alternate sensors. It can be tactical, like relocating assets or activating decoys. This adaptability means the attacker must keep applying pressure. And continuous pressure is hard to sustain. Every sortie risks aircraft. Every missile expended is expensive. Every day the campaign continues is political exposure. So an IADS does not need to win the air war in the old sense. It just needs to make the air war expensive enough to shape outcomes. This is why you will hear militaries talk about air defense in terms of protection and survival rather than guaranteed kills. And IADS is not a perfect shield. It is a system designed to keep the defender alive long enough to matter. If you take one thing away, it should be this. An integrated air defense system is not a weapon. It is an ecosystem. It sees through multiple eyes. It thinks through multiple nodes. It fights through layered shooters. And it survives through redundancy, mobility, and discipline. Defeating it is possible, but it is never simple. It requires coordination, tempo, deception, and sustained effort. And even then, the goal is often not total destruction, but reduction. Reduction of coverage, reduction of confidence, reduction of freedom of action. Because once the IADS is no longer credible, the attacker gains options. And options are what air power is about. Until that credibility is broken, airspace remains contested. And contested airspace changes everything. It forces caution, it slows momentum, it increases cost, it shifts decision-making. Integrated air defense systems do not make air power obsolete. They ensure air power is never taken for granted. And in modern warfare, that single fact can shape the entire course of a conflict.